Okay, this is the fourth and final installment of the Faraday's Law practice problems that I put together in a packet. This one's definitely the doozy of the four, so let's jump into it. The setup is that we've got a wire carrying current to the right, and that current is growing linearly with time. There is a square loop fixed in place to the side of this wire. It's at a distance A from the front edge, and the wire is at a distance A plus B from the bottom edge, A plus B. Now, if you look at what the problem is asking first, it's asking for the magnetic field as a function of distance caused by this wire. And that's the first clue that this is not going to be a straightforward flux calculation like some of the other problems were. This is a good way to practice Ampere's law. If you think about how we did the derivation for a long straight wire, you surround that long straight wire with a circular Amperian loop, and that Amperian loop has a circumference 2 pi r. This looks a little bit different from the previous times that we derived using Ampere's law the field from a long straight wire, but that's only because CT has replaced what we usually just wrote as I. I'm going to go ahead and start drawing a little bit of magnetic field lines up here now that we know what the field is. Above the wire, you get field lines that point out of the page, and below the wire, you get field lines that point into the page. So having done that, I think it kind of makes sense to conceptually talk about the direction of the induced current, and we might as well talk about the direction of the induced force as well. So I'm going to do that next. At time t equals 0, this loop is not seeing any magnetic field at all because the initial current is 0. But as the time starts to grow and the current starts to grow, then this magnetic field starts to grow and the loop sees more and more and more field lines pointing into the page. The current induced in this loop is going to seek to oppose that change, so it's going to want to try to make magnetic field lines that point out of the page, and so we get a counterclockwise current. As for the force on this loop, I find this one kind of interesting. Because if we again go with this idea of there being a magnetic equivalent of inertia, then the response of this loop to this growing field is to want to get away from it. That's one way to make the flux through the loop get smaller, is to get farther away from it. So we kind of intuitively expect a force that points down. Of course, there's always a different way of looking at it, which is to say that the top segment of the loop, because it carries currents to the left, is inside a magnetic field that points down, and so it experiences a force that points toward the bottom of the page. The bottom edge of the loop is carrying a current to the right, and it is also inside that into the page facing magnetic field, so it experiences a force up. However, because this field changes with distance, then the downward force from the top loop and the upward force from the top loop are not the same. This one wins. We can use that same kind of reasoning, the fact that the magnetic field varies with distance, to start to think about why it's going to be a little bit tricky to compute the flux in this case. If you imagine drawing some little tick marks along the side of the loop, you know that the field is weaker as you go down the tick marks toward the bottom. That means that in the flux integral, you're not going to be able to take the magnetic field out of the integral. It varies spatially. I think this bears repeating. Because the field has this kind of form to it, it varies spatially and therefore has to remain inside this flux integral. We know that the magnetic field can be plugged in from this expression that was derived previously, so the task remains to figure out what the heck dA looks like. A clever choice of dA is going to be one for which that little area has a field that does not change. The clever choice then is to choose some thin strip that runs horizontally as our dA. This should make sense because every part of that thin strip sees the same strength magnetic field from the wire, because every part of dA is the same r distance away from the wire. In the usual way of these things, we're going to call the thickness of that strip dr, the infinitesimal distance r, and the width of the strip is going to be just b. Again, to re-emphasize the difference between spatial and time integrals and spatial and time derivatives, I want to point out that for the purposes of the flux, it doesn't matter that there's a variance on time. So time, for the purposes of this integral, can be treated as a constant. All that remains is to figure out the lower and upper limit of this fairly simple integration. The dA that is closest to the wire is at a distance a away from it, and the dA infinitesimal strip that is the farthest away is at a distance a plus b. Because I'm already running out of space, I'm just going to replace that with the current I and just put in a capital R everywhere. Again, part of my space-saving measure was just pointing out that because this thing is linear with respect to time, then I can just avoid doing the time derivative on paper by just taking out the c. But it's still worth pointing out that we first had to do a one-dimensional integral to get the magnetic field, then a two-dimensional integral over the entire loop to find the flux. We had to figure out how this thing changed with time. That ultimately stemmed from the current. And then finally, we took a time derivative and divided by resistance to get this overall current. The final question asks, what is the value of the force on the loop? Well, if you think about it for a moment, we don't have to worry about this segment or this segment because of the cross product canceling out the effect of those two forces. This current points up inside a magnetic field that points into the page, so that force is to the left. This has a current that points down towards the bottom of the page, magnetic field into the page, force to the right. So the force from the left and right parts of the segment cancel out. They're exactly the same strength, even though they see a gradually decreasing field from top to bottom. As already indicated from here, we do have to think about the fact that there is a stronger repulsive force up here and a weaker attractive force here. So this is the stronger force from the top, and this is the weaker force from the bottom. The one thing that's relatively clean about the rest of this algebra is that both of the top and bottom segments have the same induced current in them. After all, it's the same loop, and these two segments are in series, so it's the same current. Both of the segments have the same length L, so I can kind of factor both of those things out.
We get the wire currents from here. We get the two magnetic field strengths from here.
Notice here that I've replaced the generic variable distance r with a in the case of the top loop and with a plus b in the case of the bottom loop. All that remains is just to collect the like terms and try to clean this up as much as possible. So this is it. This is like the big granddaddy of these kind of problems because it involved a one-dimensional spatial integral over here. It involved a two-dimensional spatial integral here. It involved a time derivative to get the current. And it involves kind of some nasty algebra down here to get the force. Another thing that I've seen problems like this do, instead of, for example, finding the force, they might ask for, energy dissipated. Obviously here you wouldn't be able to do energy dissipated for all time, 0 to infinity, but if this had been like an exponentially decaying current or something, you could calculate the total energy. So you'll see a few variants of this from time to time, and it's a hard one, but I feel like this is one that's really, really worthwhile to practice, because once you can go all through these steps more or less by yourself, then you know you're golden for this section.